All right, so yesterday we finished up talking about nucleophilic addition, and we said that aldehydes and ketones have these resonance structures which makes that carbon a good electrophilic position, right? And ketones are a lot less electrophilic than aldehyde for two reasons. One is sterically, it's harder to access, and second is hyperconjugation, right? If we think about the ketone on the bottom, that positive charge is a lot more stabilized from hyperconjugation, which means it's less reactive. The two mechanisms for nucleophilic attack are either the basic mechanism or the acidic one. The basic one basically says we're just going to come up with a strong enough nucleophile where it will slam into that electrophilic center. And when you do that, you go through this anionic intermediate that you can then protonate, but we oftentimes have very little regiochemical or stereochemical control, so we end up with the racemic mixture. For the acidic mechanism, which is similar to the pod, you protonate, and then that makes that carbon a lot more electrophilic. Oh, I don't know what that is. And then your nucleophile can attack in. And if your nucleophile is negatively charged, you don't have to do a deprotonation, but if it's neutral, then you have another deprotonation step. The most important things to remember are that these reactions are typically considered equilibrium reactions. The position of the equilibrium depends a lot on your nucleophile and your electrophile. So if your nucleophile is really strong, it tends to favor the products, and if your electrophile is really strong, it tends to favor the product side. Like I said, aldehydes tend to be the strongest electrophiles. And then I gave you guys this big list of nucleophiles. We're going to cover a lot of these. I know it can be pretty overwhelming looking at this list. In particular, this guy over here, we're going to spend a little bit of time talking about. That's called a Wittig reagent. So let's talk about just some oxygen nucleophile reactions. And let's talk about something called a hydrate. A hydrate occurs when you take an aldehyde or a ketone, it doesn't matter which one, and you react it with water. We run into this equilibrium, just like we saw before, and you can get water to add across. And you form a hydrate. Like I said, the position of the equilibrium depends a lot on the electrophile. So which is more likely to form a hydrate, an aldehyde or a ketone? Aldehyde, it's the stronger electrophile. However, there are some ketones that are really, really electrophilic, and we'll talk about some of those odd examples. So let's take a look at an example comparing aldehydes and ketones. The first one is acetone plus water. You can form, actually I'm just going to do it this way, your hydrate. However, the equilibrium is 99.9% on the ketone side. So really the hydrate is a minimal amount in solution. It's hard to even detect. However, if you take formaldehyde, it's almost impossible to isolate pure formaldehyde, which means normally when you get formaldehyde, it's actually the hydrate. And in this case, it's about 99.9% on the product side. And like I said, that's just simply because this is much more electrophilic. So let's take a look at the mechanism. And the mechanism is just going to be a review from yesterday. And we'll do acidic first, and then we'll do basic next. So let's just do the one for formaldehyde, since we know it forms a hydrate really easily. And we're going to show this with equilibrium arrows. So the first step is going to be protonation of the oxygen. And then the next step is going to be water attacking in. We're going going to kick up electrons onto the oxygen. Our nucleophile, because it was neutral, still has that extra proton on there, so we need to get rid of it. And so a second equivalent of water can reach around and deprotonate to give you your final hydrate. So it's a really straightforward, easy mechanism to remember. Does that make sense? Let's do the basic one just for review again. All right, so for the basic mechanism, if we have formaldehyde, you can have hydroxide immediately attack into your electrophile before protonation. And then what do you think the next step is going to be? Yeah, just protonate it with water. Make sure when you draw this step, though, that you don't have any hydronium around because it's under basic conditions, right? Oftentimes it's tempting just to write H+, but try to show it with water if you can. And there we go. Let's take a look at the weird example with ketones. We said ketones are a lot less electrophilic, but it does depend on the ketone. So weird ketones can form hydrates. More easily. So the first one I've got is our acetone, which we said doesn't really form hydrates very well. It's relatively inert. And then we've got the fluorinated counterpart. The fluorinated counterpart really is happy to accept a water attacking in, and why is that? Induction. Exactly. If we look at this compound on the right, it's hogging electron density, wrong way, from that center carbon, which means that this carbon is way more electrophilic due to induction. So you will occasionally run into these ketones that do form hydrates, but for the most part, hydrates are formed anytime you're working with an aldehyde. Does that make sense? I know a lot of this kind of seems repetitive. All right, so now let's take a look at, instead of hydrates, something called acetals and hemiacetals. Hydrates are where you have water as your nucleophile. Acetals are where you have any alcohol as your nucleophile. So it could be methanol, ethanol, you name it. So let's take a look at the overall reaction for this. And you guys actually did this one in your pod, so you know it's not too bad. At least you got halfway there. And I'll just put in my catalyst, and we'll assume this is done under acidic conditions. And just like with hydrates, you're going to get these two carbon-oxygen bonds where your carbonyl used to be. And you also have water as a byproduct. This is our acetal. One key thing that I did want to point out is the acid source. Your acid's conjugate base should be non-nucleophilic. So what's a good example of an acid where the conjugate base is non-nucleophilic? Yeah, sulfuric acid, we saw that on the pod. What's another one?
H3PO4.
Yeah, phosphoric acid. So sulfuric acid, phosphoric acid, or tosylic acid are usually the most common. So let's put those down. And tosylic acid, if you remember our tosylate group, looks like this. It's a relatively good organic acid that's pretty gentle. So you can use either of these. It really doesn't matter too much, but just be aware you've got to be careful what acid you choose for these. So let's go through and do the mechanism, but what I want you guys to do is, now that you've already seen the basic and acidic mechanism a few times, is try to figure out the mechanism on your own and then check with a partner, and I'll give you guys a starting material to work on. So let's do this one. And let's assume we have H plus and we've got methanol. So go through and see if you can determine each intermediate that you would get along this entire reaction. I'm going to pause this too. All right, first reaction, fastest reaction in chemistry, acid base. All right, so we're going to protonate our ketone. That's not too bad. All right. If you got that far, that means you're on track, right? What's the next step after we protonate our ketone? Yeah, the methanol can attack in. That carbon is now super duper electrophilic, which means that this methanol has no problem attacking in as a neutral nucleophile. Okay? So now we've got this over here. What do you think is going to happen next?
Deprotonation.
Yeah, deprotonation. Okay, methanol is a weak base. Whoop. So what we can do is just have it grab this proton, clamp down. It's our homie. All right, and then what's the next step? Yeah, protonation of your OH group, right? Okay, so we've got this protonated methanol, which is pretty handy because that's our acid that's been regenerated. So this alcohol can come grab a proton back from our methanol. And now is the tricky step. How does this water fall off? Does it just fall off on its own?
I'm guessing it's attacked by the carbon below. It's attacked by the methanol we just had.
So there's a couple different routes that people can draw, right? One option is to have your nucleophile attack in and shove off the water, SN2 style, but I'll tell you that that's not going to happen. Why do you think it won't happen that way?
Tertiary.
Yeah, SN2 rules say that crowded electrophiles have a really, really hard time doing SN2. Sterically, it's blocked. So what ends up happening is something that I call a malicious shove, where that lone pair can clamp down, or alternatively, you can show the water falling off and being resonance stabilized. Either way is acceptable. Because this has its own resonance structure where that positive charge is shared between the carbon and the oxygen. Why do you think I prefer the positive charge on the oxygen? Full octets, right? So that would be our major resonance contributor. Okay, perfect. We're on our way. Now we've got methanol around. What do you think could happen?
Repeat.
Yeah, I can repeat that attack. This carbon is still electrophilic because that oxygen has a formal positive charge. We can kick up electrons onto that oxygen. And then last but not least, we can deprotonate that using our methanol or our water. It doesn't really matter. And you end up with your acetal. So it's important to remember that water is our byproduct. We're kicking off water in the reaction, and it's not a part of our final product. All right, there is some terminology that I wanted to go over. Like I said, this is our acetal. It's our final product that we get from this equilibrium. There is a step, though, that has an important name. This is called our hemiacetal. What does hemi mean? Half, right? So we're halfway to our acetal. You'll oftentimes hear this term in biochemistry. Our pod yesterday, your final product, if you look at it, has an OH group coming off of it, right? So glucose in its closed ring form is an example of a hemiacetal. However, there are a lot of reactions where you do form acetals where you can keep on adding more alcohol groups in. In the case of glucose, you stop at the hemiacetal. In many situations, you do not. All right, now another abstract question. Let's say I'm at my acetal and I want to go back to my ketone. What should I do?
Can you have a base to it?
You want to
Maybe.
turn one of your methanols.
Give you a hint. Think back to last year or Gen Chem whenever you took Gen Chem.
That's what we were talking about.
Well, if it's Gen Chem, then it'd be like Chatelaise.
Le Chatelier's principle?
Yeah, that thing.
Okay, so Le Chatelier's principle, how can we shift this equilibrium back to our starting material side?
Water.
Add in a bunch of water, right? If we flood this reaction with water, we will favor the ketone. What if we want to favor the acetal? What can we do?
Dehydrating.
Yeah, remove the water from the reaction. So this is commonly how we can favor formation of our acetal or a ketone, is by how much water we put in or remove from the reaction. A simple way of removing water is distill it off, right? So if you're running this reaction, have it in a distillation apparatus and then just distill water as it's produced, and that will drive the product towards the acetal side. So let's make a note of that. Good old Le Chatelier's principle. One thing I will say with these reactions is be certain that you can do them forward and backwards, right? Because it's an equilibrium reaction, you should be able to show it going both ways. So a good test at home to make sure that you understand this is start with the acetal and then see if you can do the opposite reaction. So acetal plus water and acid should be able to get you back to your ketone. That's a really good test at home. All right, now getting on to some trickier stuff. We've got a fancy acetal. So let's say we've got just a generic ketone. And we've got this guy. What should we call this?
Ethylene glycol.
Ethylene glycol. That's the most common name for it. And if we react this under acidic conditions, so like a drop of sulfuric acid, what do you think we'll get out? I gave you guys a hint in the name.
It's a cyclic acetal.
Is it going to be a 5 or 6 member ring? 5. If we look at this, basically this group was added on, right? Okay. And then our byproduct, just like we saw before, is going to be water. This is our cyclic acetal. I've got a question for you guys, though, that's a little bit more abstract. Why does it form a ring system as opposed to having 2 of your diols attack in? So what I'm asking is, why do we get this? And, whoop, oh no. Instead of something that looks like this. Does anybody have an answer for that?
Prettier.
It's easier to draw?
Sterics?
Sterics?
Wouldn't that just OH be closer to when it's ready, when the carbon's ready to attack, it would just be closer. So you don't have to, because the other one's the one's floating in space, the other one's still attached to the carbon. So when it becomes available to be attacked by.
Yeah, I think that's a great explanation. Once you form your hemiacetal, that oxygen dangling off the end is in close proximity. Another reason is entropy, right? It's a lot easier to go from 2 moles to your product than 3 moles to your product, right? Entropically, that's a lot more favorable. So either explanation is a good rationale for why we get the cyclic version and not this version I've drawn below. All right, so you may be wondering, why are you showing me this? This is really just a protected ketone. So for example, I can protect a ketone, do a bunch of chemistry that might react with the ketone otherwise, and then remove it later on. So let's say I have a ketone I don't want to react on my molecule, but I want to work with a Grignard reagent. I can protect it with this method, react my other stuff with the Grignard, and then deprotect it later on. And I'll show you guys some examples of that later. So let's briefly do the mechanism for practice. And just like before, I want you guys to try to figure it out on your own first, and then we'll double check as a class. There should be 8 total, just like before. And refer to your notes if you're stuck, too. Well, starting material plus 7, I should say. So first step, proton transfer, fastest reaction. Now we've got ethylene glycol floating around. What now? Yeah, it's going to attack in, kick up electrons. All right, I'm just going to shorthand this minus H plus rather than drawing a whole new diethylene glycol group. All right. Now what? Deprotonation? Yeah, we're going to protonate which position? Yeah, the alcohol coming off of our former electrophile. So I'll just write H plus. So really all we're doing is shuffling a proton around in this step. Okay, now what? The malicious shove? Yeah, not SN2. That's the key thing. Okay, so we've done this and kicked off water. That's perfect. Now what? Yeah, it's going to attack itself. And then last but not least, we'll do a deprotonation to get to our final product. So all of these have water floating around. Does that make sense? I know it's very steppy, can make your hand cramp up, but please try to practice. So let's see its utility in action. I think this example I pulled from the textbook. How can I do this transformation? When I look at this, what I'm seeing is we're basically turning an ester into an alcohol. What reagent can we do that with? Yeah, lithium aluminum hydride can be used to convert an ester to an alcohol, but the problem, it would react with the ketone as well. So what's our workaround?
ECC.
Maybe we should protect our ketone, right? That's one common mistake students make is they're like, well, why doesn't the ester form an acetal? Really, acetals only are formed with aldehydes and ketones, not esters or carboxylic acids. They don't do hydrate formation, they don't do acetal formation. So aldehydes and ketones will do it, but esters will not. Okay, so if we want to do this, I won't punish you guys with the mechanism again. You can react this with ethylene glycol, catalytic acid, and we said to favor formation of the product, we can remove water. So I oftentimes just write minus H2O to indicate we're distilling water off in this process. Now that we've done that, we're primed and ready to go. We've got our acetal installed, our cyclic acetal. We said lithium aluminum hydride can be used as our reducing agent, followed by H2O wash to protonate it. And then how can we remove the protecting group? Add more water, right? So in this case, you can oftentimes do this last step in one go by just having dilute acid around. So the key is using Le Chatelier's principle to your advantage. Does that make sense? Okay. Let's continue on and talk about nitrogen nucleophiles really quick, because I think that'll help you with the pod. The pod has a nitrogen nucleophile. So this is really similar to oxygen nucleophiles with a few twists. This time I'm going to use an aldehyde as our starting material. And I'm going to use an amine, and I'm going to label it as a red R. And just like before, this is under equilibrium conditions. I'm just going to do acid. And when we do this, we are going to form a new functional group. Let me clean this up. And this is referred to as an imine. It's basically the nitrogen version of a carbonyl, right? So it's got a nitrogen carbon double bond. These are really common reactions. One particular thing I did want to note is that this reaction is really sensitive to pH. Why do you think we can't just throw in super strong acid? Yeah, the amine is basic. If we have this at too low of a pH, the amine's protonated, it won't act as a nucleophile and the reaction won't occur. So you actually have to run this typically under buffered conditions. And typically you want to run it at about 4.5. That's the one big difference between nitrogen nucleophiles and oxygen nucleophiles. All right, so let's take a look at this. One thing I will say is depending on the textbook that you look at, the mechanism may differ in the proton transfer steps, so just be aware of that. So we've got our aldehyde, and we've got our amine. Actually, I'm just going to keep the color scheme going. And we've got our acid. All right, so the first step, I'm going to show it a little bit differently than the Klein textbook. Don't freak out. I'm just trying to keep things consistent. Is protonation of the ketone. In reality, the equilibrium is a lot more complicated, right? Because we've got another base present. However, this is going to make it more consistent. And then we've got this amine nucleophile floating around. This can attack in, kick up electrons. This nitrogen has a positive charge. What next?
Deprotonation.
Yeah, deprotonation. And then what now? Yeah, protonation of the alcohol. This mimics our acetal reaction where we need to turn that alcohol into a leaving group. Okay? Oh, let me keep this blue. All right, and then we've got our malicious shove, just like we saw before. That can kick off our water. Oops. Sorry, we've got a proton coming off. And then last but not least, we're going to deprotonate. And we're going to retrieve our imine. There is conflicting experimental evidence about this reaction. If you read through the section in your Klein textbook on the mechanism, there's a lot of evidence that the carbonyl is actually not protonated. However, I'm just going to try to keep it consistent to avoid any confusion, if that makes sense. All right, there's a slightly different reaction that occurs if you use a secondary amine. So the key thing to note with this reaction is that this is a primary amine. If you do a secondary amine, you run into a problem. Why is that?
You can't deprotonate a carbon.
Yeah, you can't deprotonate a carbon bond, right? So let's take a look at a workaround for this. Okay, with secondary amines, you form something a little bit different. Actually, I'm just going to keep it the same as last time. just keep this as an R group. And we've got acid around. Actually, sorry guys, I'm going to change this just to a CH3. Sorry, I'm messing up all your notes, I know. Instead of forming an imine, you form an enamine. The way I remember the difference is this one has an alkene, so we've got the ene in it, right? Alkene for ene, and then amine for the amine coming off of it. An imine oftentimes is confused with an enamine. Make sure you're using the correct terminology. And you get these anytime you're working with a secondary amine. All right, I think we have enough time to briefly go through this mechanism. So we'll keep it consistent. Like I said, the pH matters a lot, and the mechanism may differ a little bit in the textbook, but I'm going to try to keep it less confusing for you guys, if that's a thing. Oh, it's implied, but I'll put it in there to make you happy, though. All right, so we've got acid around. Just like before, we can protonate our carbonyl. And we've got this amine that can act as a nucleophile. So this is going to swing in, attack, kick up electrons. Actually, I'll draw them all out here. We've got our nitrogen with the positive charge. Next step is our deprotonation, so I'll do minus H plus. Now this nitrogen's a little happier. This is essentially our nitrogen equivalent of a hemiacetal. And then the next step is going to be what?
Protonate the alcohol.
Yeah, protonate our alcohol. So I'm going to put in a kind of crooked equilibrium arrow. And then we start getting into interesting chemistry here. We still have this lone pair, which can do a malicious shove. So we'll clamp that down. Oops, this should be a positive charge. And actually, I'm going to clean this up a little, which is our hint. We can't isolate this as a positively charged compound because what might happen?
Get attacked by
I just get probably about.
It's tempting to say, well, maybe another equivalent of amine can come in and you can form like an acetal-like group. However, sterically, that's really hard. It gets blocked up pretty quickly with our secondary amines. So instead, what happens is this oxygen is going to grab one of these protons in our beta position. It's going to domino down. And that will give you your enamine and regenerate your acid. So that's essentially why your enamine forms is you don't have a proton off of that nitrogen to deprotonate. The next best option is that beta position proton. So you really can only form enamines when you have available beta protons. Yep.
Will this work if you have an R group instead of CH3?
So that R group, if you have it, has to have a proton coming off of that position.
So if it was just a bond to a C, that it was just CH2 bonded to more carbons down the line.
Yeah, so for example, let's imagine we had up here, instead of a methyl group, an aromatic ring. Then we couldn't form an enamine, right? Because that aromatic ring wouldn't have a proton on it. So that's a good point.
If it was cyclohexane, it would.
If cyclohexane, we could. All right, I think that's where we'll stop today. Tomorrow when we come in, we'll talk about a cool variant of imine chemistry.